All right. So basically, one thing I point out is just when you want to see like how long it takes an operation to occur, like a Python operation, you kind of need to like think through how is Python doing this under the hood, right? Like if you do 6 in elements, right? It's like, oh, it's just one step. But obviously, right, to determine whether or not this number 6 is in this list here, like what does Python have to do? All right. Now with lists, just plain old lists, generally what it needs to do is go one by one. All right. We'll expand upon that in the future, like later in the course. But for now, like you can think of just, okay, I can check every single element and see, does this number equal 6, right? So let's just do that. For element in elements, if the element equals the target, right, like the number 6, then we want to exit, right? So we'll just return true. If we get to the end of the list and there is no 6 or there is no target, right? We loop through all the elements and we haven't returned true yet, then we want to return false. Okay? So you can see here we have is the number 6 in the elements. That should give us true, right? Because it's there. We have to with the number 9, that should give us false, right? So let's see if we did it right. Okay, that looks good. All right. So what is the cost of something like this? All right. Well, it's essentially one check, right? This if statement, one for each element, right? So essentially, how long does it take? It's 6 operations, right? 6 checks. So when you do 6, is the number 6 in elements, and this is our list, right? This costs us, we can just say this costs us 6, except when it's not there, right? Then it costs us 6 plus 1, right? Because we loop through all of them, and then we return false. Right, so this, we kind of have 1, 2, 3, right? Every time we check it. And then I guess even when it does, and we get to the end when it's not in there, and then it returns false. So we get 6 plus 1. All right. So one thing to note is just that as we expand the length of this list, right, this cost is going to increase, right? Now my list is 1, 2, 3, 4, 7, 9 elements. So the cost of checking each one is really 9 plus 1, right? So really, when you ask like how costly is this operation, it depends on the length of the input, right? Depends on how long this thing is. So this is pretty typical when we're calculating how costly our operations are. We express it, they're going to generally depend on the length of the input oftentimes. And so because of that, we express the cost in terms of the input, right? So we say, okay, our input is n, right? Input size. We'll describe that as n, or like number, I guess. And then we'll say the cost of this so far is n plus 1, right? The cost of our is n plus 1. Now, one thing that maybe is in the back of your head, which is like valid, is, all right, well, this is the cost when there's no match, right? Right? We have to go through all of the elements, say there's nothing in here, and then return false. But what if actually we're looking for the number 6 and we move it here, and then what's the cost going to be? Well, I go through the first element, for element in the list of elements, and you say does 6 equal 6, and we return true. So in that case, it seems like the cost actually is like 1, right? 1 or 2, right? Are you guys following this so far? Any questions about this? Okay, so we kind of saw that really, like, it seems like the order, or like we need to look at the specifications of this to, the details of our input to figure out how much does this thing cost? Like it's not so simple. So it turns out when you do big O notation, right, there are different things you can kind of consider, right? Like the Goldilocks principle. So you can kind of like say, okay, what's the best case scenario? What's the average case scenario? And then what's the worst case scenario, All right, so we just saw, I guess, like the best case scenario is that the number 6 is here right off the bat. The worst case scenario is our target element simply isn't there, or it's at the very end. Okay. All right, so which one should we choose? The best case scenario, when we're trying to figure out like how costly, the thing about why we care if something's costly is because we don't want to do it, right? It takes too long, right? Or we want to try to find a better solution that doesn't take so long. So when our technique, whatever technique we choose, under the best case scenario, it's not going to be that costly, right? If our technique is to ask a small child if the number 6 is in this list, and then the number 6 is the first thing, we're okay. It'll take like a few seconds or maybe a minute, but we're still okay. All right. When things become problematic are under non-best scenarios. Okay. So we don't have to worry about the best scenario because there's not really a problem under the best case scenario. The average case scenario, that from a practical standpoint, I think that's a fair point. Like, shouldn't we take a look at our data and see on average where these numbers show up, or like the order of them, or maybe we'll just take an average of all the times we ran this operation and see how costly it is. Right there, we could say, why don't we just do it that way? The reason why we don't is because we would have to get external data to do that. Like, if we're just writing this program from scratch, if we're like inventing a new web application, we don't have users yet. We don't have practical data at this point in time, right? And it is challenging lots of times when you're coding to be like, wait a second, now let me pull all the data and run it through this thing, right? You could do it, but that's not the technique with big O or calculating time complexity. So we don't use the average. The point is we don't use the average case simply because it's too difficult to get that data, right, and to run it through the system. Instead, we choose the worst case. The worst case, we do not need external data to choose, right? And it matters, right? It matters. It may actually be costly or take too long for us under the worst case scenario, in which case we want to try to, improve our operation. Okay, so again, like the worst case scenario, how do we figure out the worst case scenario? We're trying to see, is the number 6 in this list? Just move 6 to the end, right? Assume 6 is in the last spot, or assume it's not in there at all, in which case we'd have to check every element, and that would be as costly as this operation gets. Okay, so this is like the first thing about time complexity, right? Is, I guess, one, you have to think about what's going on under the hood, right? And we'll like show, walk through some of that for you. But what's going on under the hood when you call these different operations? And then two, you're always assuming the worst case scenario. We'll keep going, but before we do, questions about just these 2 points. All right. Okay, so then the next thing. Yeah, okay, so we saw this operation, this is in, right? Let's say, and this is the cost of, I guess, seeing if an element is in our list, if the target is in our list. The next, let's say we have a different task, and this task is, given a list of numbers, like 1, 2, and 3, we want to find all products, right? So you can see what I did here is like 1 times 1, so the first number times itself, the first number times the second number, the first number times the third number, right? Then the second number times the first number, second number times itself, second number times the third number, right? So how would you do something like that, right? You use a nested loop for every single number, right? And you can go through, this isn't the main point, but this is just an example, but this is how you would go through it, right? For every single number in this list, go through every single number, right? For number 1, 2, and 3, starting with the number 1, go through the numbers 1, 2, and 3 and multiply it by that number 1. Then move on to the number 2. And for the number 2, go through the numbers 1, 2, and 3. So in other words, 3 times, you want to go through 3 elements, right? So the cost of this is 9. 1, you can count these out, 3, 6, 9, right? And in terms of n, the cost of this is going to be n squared. The easiest way to figure that out, and we'll talk about this some more, but the easiest way to figure that out is simply to count the number of nested loops, right? So for each element, right, for every element, there's our n, perform an operation n times, right? So do n times, so n times perform n. And we know n times n, right, is going to lead to n squared. Okay? Okay, here's the second point, which probably after a pandemic, we all know this. Exponents are exceptionally important, right? So, like, how big a deal are exponents? Like, right, just like to give you an example, if our cost is n, right, and we have only 100, our input size is 100, right, the cost to perform the operation is 100, right? 100 is nothing, right? Like, having 100 customers, you can you can hardly run a business. But still, if your cost of the operation is n squared, that takes 10,000, right? Once you do 2,000, get to 2,000 customers or 2,000 clicks or whatever, if you have an operation that takes n squared, well, you're up to 4 million very quickly, right? 10,000, we're up to 100 million. In other words, right, these exponents are a huge deal. They're such a big deal that they're basically, that essentially I'll break this down, but the largest exponent, say we calculate the time complexity and we get something like this: 5n cubed n squared plus 100n plus log n plus 100. The only thing we care about is the largest exponent. Okay? When you're expressing time, when you're saying what is the cost of a function, you only have to consider the largest exponent. I just want to show you why that's the case. Say the cost is something like this: n cubed plus n squared, right? And our n is 1,000. So I just what I do is I perform each of these. These are called terms, right? Whenever you separate these values by a plus sign, we would say this has 4 terms. 1, 2, 3, 4. I guess 5 terms, right? The number in front of the n, that's the coefficient. The little number up top, that's the exponent. All right. So when we're calculating big O, we don't care about the coefficient. As we'll see, they don't matter. They don't move the dial. And we also don't care about what's called like lower order terms. Lower order terms are terms that are less than the leading exponent, than the highest exponent. So these 4 are all lower order terms. All right? Why don't we care about those things? Well, if we take this operation and we just put an input of like 1,000, which again is nothing, right? This thing is, I don't know what it is. It's there's 3 zeros, 1,000, million. I think it's either 100 million or a billion, okay? By getting up to n cubed. This here is 100,000. So 100 million versus like 100,000, like it's nothing. Once we get to n, right, it's only 1,000. Once we get to np log n, once we get to log n, it's 6. It's just nothing. And here, I think this was only, and then of course, that last 100 doesn't do anything. So if you take this value, right, and we add this up and just like see it, you can see this n squared only comes in a factor at the, like, I think this is like 1/1000th essentially of the total. Let's just take a look. Total cost. Let's do this value divided by this. Yeah, so it's 1/100th, 1/1000th, about essentially 1/1000th. Okay, so at just a very small input size, already this n cubed just dominates everything else. So because of that, we can just simplify things and we don't need to worry about these lower order terms. All right, it's the same thing with the exponents. Moving up by like a factor of 10 or even 100 is not a big deal. Or sorry, by the coefficients I said. Multiplying this by like 10 or 100 doesn't really matter. The only thing you care about are these numbers here. Okay, so we would say the big O, even if something starts, but we're like, okay, actually the cost is this. When you say what the big O is, you say it's n cubed. And you just forget about everything else. All right? Why? Because it doesn't matter. It just doesn't matter. It's not going to make a difference. Okay. So if you read the definition right on Wikipedia, it says the time complexity of an algorithm quantifies the amount of time taken by an algorithm to run as a function of the length of the string representing the input. In other words, as a function of n, right? We talked about that, why that matters, because the larger the n, the larger the cost. And then it says the time complexity of an algorithm is commonly expressed using big O notation, which excludes coefficients. Coefficients are the number, like anything up front, like the number 5 here, or the number 100 here. So we don't care about that. And it also excludes lower order terms, right? So we don't care about these things either. We only care about the term with the leading exponent. All right? Questions before I move on from there. So the point so far is that exponents are an enormous deal, right? As we know. And they're such a big deal that we only care about the dominant exponent, right? The highest order term when expressing the big O of a function. Okay? If you, so how do you know kind of what this term is? You just count the number of nested loops, right? So here, if we go through, a set of elements, what is the big O of this? Well, this is a nested loop, so it's n squared, right? So this should have a cost of 9. And we count these up, 1, 2, 3, 4, 5. Oh, whoa, it's more than that. Is that because I'm printing it? I think, why don't I just print it here? It's probably 18 because I'm printing it twice. Yeah, now I have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. One thing to note is that this is not a nested loop. If I do this, right? What's the cost here? This is for each element in the list of elements, print I. That's n. So this thing right here has a cost of n. And then a second time for each element in the list of elements, print I. So then this is the cost of n, right? So what's the total cost here? 2n, right? 2 times by n. Sorry. So the cost would be 2n, but then we don't care about coefficients, right? So really the big O is n. And let's just see that, right? You can see that this goes down to 6. All right? What if we, these nested loops can keep going. So we can, have a nested loop here. 4 ion elements, 4 ion elements, 4 ion elements. All right, what's the cost now? It'll be n cubed. For each element, go through each element. And then for each of those things, go through each element. So 3 times 3 times 3, right? Which is, I guess, 27. Let's just see it. All right, so I'm guessing this is 27. All right, so this cost is n cubed, right? So you just have to, really what you're doing is you're just counting the nested loops. And be careful about loops that are not nested, right? What's the cost of something like this? For I, let's say we print I. And then we have this. So the cost is going to be n here for the first loop plus n squared. And then again, we don't care about the lower order term. So the real cost, the big O, is n squared. I think that's all. Oh, and then the last thing is, what if I do something like this? For each element, ask it in press to like a target. For each element, it's kind of weird. Ask is a target in the elements, right? This may look, if you just count the number of loops, you'll be like, oh, well, this has a cost of n. But remember, inside this, every time we call this in element, the in operation also has a cost of n. So you're performing n times, you're performing an operation that has a cost of n, so the big O is going to be n squared. So you just have to be careful about these operations that have hidden loops inside of them. All right, so far, this is basically all the points that I need to make about big O. So what were those points? It was, okay, we always choose the worst case scenario when we're considering it. You have to consider kind of what's going on under the hood, right? We only care about the highest order term, meaning the term that has the highest exponent, and we do not care about coefficients, meaning any number you might multiply that by, right? And we said to calculate big O, you count that you care about the number of loops, right? Especially nested loops. All right, so if you have just 2 loops, you care about the one with the most amount of nesting. So this has more nesting. This is n squared right here, and this is n. So n plus n squared reduces down to n squared. All right, questions about this material? No? Great. Yeah, let me know. You don't have to get this in like 15 minutes. All right, so here's time complexity, big O. I thought there was I think it says brute force and then brute force lab. So move through these. Then let's say, go through SQL views, do these readings. This should, I think you'll be able to understand this. And then move through these brute force lessons as well. Again, this is kind of like rudiments. Like, even though we don't like writing out nested loops, in interviews, when you're like, how do I solve this thing? Just doing the thing that logically is easiest, even if it's not time efficient, you want to be able to lean on that. So performing a nested loop can often come up, and it's not as easy. You don't want to do it for the first time under an interview. Let me put it that way. So it's worth moving through it here. You'll see it probably will take a little while to get the hang of it if you haven't done it in a while. All right, so then we'll move on to that section. I'm pretty sure that's all we'll cover today, but then what's next is when we start moving into cloud computing. Oh, I should undeploy this. Sorry about that. Yeah, I guess I deployed a lot. All right. Questions before I move you into breakout rooms? Yeah? Okay.